Hello and welcome to G Fun Facts Online, the show that delves into the amazing science that shapes our world and the universe around us. Today, we're setting our sights on the single most important object in our solar system, the one thing our entire existence revolves around. Quite literally, we're talking about the sun. For all of human history, we have looked up at that familiar fiery orb. We've worshipped it. We've studied it. We've used it to mark the passing of our days and seasons. It's the constant, unwavering engine of our world, so familiar that we might think there's not much left to learn. But science has a wonderful way of showing us that the most familiar things are often the most mysterious. In a truly remarkable feat of astronomical observation, scientists have just captured the sharpest, most breathtakingly detailed images ever taken of the sun's surface. And what they found is completely reshaping our understanding of the fundamental forces that drive our star. We're not just talking about a clearer picture. We are talking about discovering ghostly, shimmering structures that were predicted by theory but had remained completely invisible to us until now. Imagine you've been looking at a masterpiece painting your entire life from a distance, and suddenly someone hands you a magnifying glass so powerful you can see not just the brush strokes, but the individual fibers of the canvas itself. That's the leap we just took in understanding our sun. So get ready to see our star in a whole new light, to see the magnetic curtains that flutter across its surface. This is the story of how we peered into the sun's fiery heart and found its hidden magnetic architecture. So how did we manage to get such an unprecedented look at our star? This incredible breakthrough was made possible by a true marvel of modern engineering. The Daniel K. Inouye Solar Telescope, which we'll call the DKIST, perched atop the sacred volcano Haleakala on the island of Maui, Hawaii. The DKIST is, without exaggeration, the world's largest and most powerful solar telescope. Its primary mirror is a colossal 4 meters or 13 feet across. A mirror that size gives it staggering light-gathering power and resolution. To put its power into perspective, the DKIST can distinguish features on the surface of the sun as small as 20 kilometers, or about 12 miles wide. Now, let's pause on that for a second. The sun is 150 million kilometers away from us. Seeing something that small from that far away is the observational equivalent of standing in New York City and being able to clearly read the license plate on a car in San Francisco. It's an almost incomprehensible level of detail, and looking at the sun with this kind of power presents some unique challenges. You are, after all, pointing a giant magnifying glass at the brightest, hottest thing in the sky. The telescope generates so much heat at its focal point that it would melt metal in minutes. To combat this, it has a state-of-the-art cooling system, with over 7 miles of coolant pipes running throughout the facility, much of it chilled by ice created on site during the night. It also uses a sophisticated system of adaptive optics, deformable mirrors that change their shape hundreds of times per second to counteract the blurring effect of Earth's atmosphere. This is what allows it to achieve those crystal-clear images. The specific instrument that captured these revolutionary images is called the Visible Broadband Imager. It was set to look at a very specific wavelength of light, known as the G-band. Think of the sun's light as a full orchestra playing every note at once. The G-band filter allows scientists to listen to just a single instrument, one that happens to be particularly good at revealing areas of strong magnetic activity. It's like putting on a pair of magnetic sunglasses, filtering out the overwhelming glare to see the intricate dance of magnetism underneath. It's this combination of raw power, clever engineering, and precise filtering that has opened up a new window onto our star, giving us a view of the solar photosphere, its visible surface, that we have never seen before. Now for the main event. The telescope is online, the adaptive optics are humming, the G-band filters in place. What did we actually see? The images revealed the sun's familiar, granular surface. This surface is made of vast, Texas-sized convection cells called granules. You can imagine it as a violently boiling pot of water, but on a stellar scale. These granules are the tops of massive columns of hot plasma rising from the sun's interior, spreading out on the surface, cooling, and then sinking back down along dark, cooler lanes. It's a process that completely resurfaces the sun every few minutes. But it was in those dark, sinking lanes at the edges of the granules that scientists saw something astonishing. They saw ultrafine, alternating bright and dark lines, like shimmering threads, rippling along the boundaries. They've been officially named solar striations, but the much more poetic and descriptive name scientists are using is magnetic curtains. Imagine vast, invisible sheets of magnetic force, thousands of kilometers long, but only a few dozen kilometers wide, fluttering like fabric in the turbulent solar wind. These are not solid structures, but patterns of light and energy. They are the direct visual representation of the interaction between the hot plasma and these rippling sheets of magnetic field lines. Where a ripple in the magnetic curtain is a little bit stronger, it constricts the plasma, making it hotter and causing it to glow brighter. That's our bright line. Right next to it, where the magnetic field is slightly weaker, the plasma is less compressed and appears dimmer. That's our dark line. This delicate interplay creates the striking striped pattern, revealing the fingerprints of fine-scale magnetic field variations that were completely invisible until now. And what is perhaps most shocking of all is the subtlety of the force at play here. The variations in magnetic field strength that create these huge prominent striations are on the order of only 100 Gauss. To give you some context, the magnetic field of a typical refrigerator magnet is also about 100 Gauss, a tiny magnetic whisper on a star's surface. A force you can barely feel in your hand is strong enough to organize hot plasma and create visible patterns larger than cities here on Earth. This discovery also confirmed a long-theorized phenomenon known as Wilson depressions. These are minute dips in the solar photosphere, just a few kilometers deep, caused by the localized magnetic pressure pushing down on the solar surface. We can now see the magnetic curtains are sitting in these tiny valleys that they themselves have carved. This discovery is so much more than just a beautiful, new feature. It represents a monumental moment for solar physics, a long-awaited handshake between theory and reality. For decades, solar physicists have been trying to understand the incredibly complex physics of the sun using powerful computer simulations. These are called magnetohydrodynamic simulations, or MHD. That's a huge mouthful, but you can think of it like the supercomputers that create our weather forecasts. Weather models simulate the interplay of air pressure, temperature, and moisture to predict a storm. Solar MHD models simulate the interplay of plasma, heat, and magnetism to predict the sun's behavior. For years, these MHD simulations predicted that if you could only zoom in far enough, you would find fine-scale magnetic structures at the edges of solar granules, structures that looked exactly like these magnetic curtains. But for all that time, it was just a theory, a ghost in the machine. Our telescopes simply weren't powerful enough to see if they were actually there. Scientists had to trust that their models of plasma physics and magnetism were correct, but they had no definitive proof. The Inouye Solar Telescope has now provided that proof in the most spectacular way possible. When the science team compared the real images of the solar striations with the images generated by their latest MHD simulations, the results were a stunning match. The patterns, the sizes, the rippling behavior, the location in those dark lanes, it was all there, a near-perfect one-to-one correspondence. This is a massive victory for science. It does more than just confirm the physical reality of these striations. It validates decades of theoretical work and proves that the complex computer models scientists use are built on a solid foundation. It shows that our understanding of the fundamental physics of plasma and magnetism is on the right track. This powerful synergy, where observation confirms theory, now creates a feedback loop. Scientists can use the real-world data from the telescope to further refine their simulations, making them even more accurate and predictive. We've bridged a long-standing gap between what our computers told us should be happening and what our eyes can now finally see. So we found some faint magnetic ripples on the sun that match our computer models. Why is this a headline discovery? Why should you, living your life here on Earth, care about magnetic curtains 150 million kilometers away? Because these tiny, fundamental ripples are the building blocks of giant, planet-sized storms. As Dr. David Kuridzi, a lead scientist on the project, explains, these striations are the fingerprints of fine-scale magnetic field variations. By finely resolving these foundational magnetic structures, astronomers can begin to trace how these small-scale dynamics accumulate, twist, and tangle to eventually unleash the much larger and more energetic solar phenomena that directly impact our lives. I'm talking about solar flares, and more importantly, coronal mass ejections, or CMEs. These are colossal explosions on the sun that hurl billions of tons of plasma and magnetic fields out into space at millions of miles per hour. When one of these solar tsunamis is aimed at Earth, it can cause what we call a major space weather event. And for our hyper-connected, technologically dependent society, space weather is a serious threat. A powerful CME can induce electrical currents in our power grids, causing them to overload and fail, leading to widespread, long-lasting blackouts. It can fry the electronics on our critical satellites, disrupting GPS, global communications, and financial transactions. It can even pose a radiation risk to astronauts and passengers on high-altitude polar flights. In 1859, the Carrington event, the largest solar storm on record, set telegraph offices on fire. If a storm of that magnitude hit us today, the damage to our technological infrastructure could be catastrophic. Understanding the sun's magnetic architecture, right down to these foundational curtains, is the key to improving our ability to predict these dangerous events. It's like trying to forecast a hurricane. You can't do it by just looking at the finished storm. You need to understand the small-scale changes in atmospheric pressure and ocean temperature that give birth to it. This discovery gives us a completely new, finer level of detail to work with, allowing us to build better, more accurate space weather models that could one day give us the crucial warning we need to protect our world. But the significance of this discovery extends far beyond our own solar system. It reaches out into the vastness of the cosmos. It turns out that magnetically induced striped patterns, remarkably similar to these solar striations, have been detected in very different and much more distant astrophysical environments. For example, we see hints of them in the enormous, cold, dark molecular clouds where new stars and planets are born. In these stellar nurseries, magnetism is the king. Magnetic fields dictate how clouds of gas and dust collapse, how fast they rotate, and how they ultimately form new stars. But studying those faint magnetic fields from light years away is incredibly challenging. This is where our sun proves to be the ultimate cosmic laboratory. Because it is so close, we can use the DKIST to resolve these magnetic structures in a level of detail we could never dream of for a distant nebula. By studying the precise physics of how these magnetic curtains form, ripple, and interact with plasma on our own star, we create a Rosetta Stone for cosmic magnetism. This knowledge provides an invaluable template for understanding similar, but much harder to see, magnetic phenomena all across the universe, from the birth of stars to the behavior of materials swirling around black holes. In a very real sense, by looking closer at our own sun, we are learning the universal language of magnetism. So, the face of our sun, an object so familiar it's almost mundane, has revealed a new layer of its intricate and beautiful personality. These magnetic curtains are not just a fascinating new feature. They are the missing link between our theories and reality. They are the fundamental magnetic threads that, when woven together, can create powerful solar storms that affect our lives. And they are a window into the magnetic processes that govern the birth of stars and the evolution of the cosmos itself. It's a profound reminder that even the most well-known objects in our universe still hold deep secrets, waiting for us to build the right tools and ask the right questions. As the Daniel K. Inouye Solar Telescope continues its mission, we can only imagine what other secrets it will uncover. We are in a golden age of solar astronomy, where the star that gives us life is finally, after millennia of observation, beginning to show us its true, dynamic, and breathtakingly complex face, one magnetic curtain at a time. Thanks for listening to G Fun Facts Online.